Today I'm going to talk about a topic, as the title would suggest, about online speech. And I'll talk about sort of, what that means from the, seemingly simple technical things that we think we might be able to easily answer to the that turn out to be really technically hard, to the questions that I think basically we don't even really know how to formulate yet. Before I get into the details of the talk, I'd like to basically just quickly acknowledge some of the people who I've worked with on this, and I'll mention them as I go through the talk. I owe a lot to my former PhD student, Sam Burnett, who's now at Google, working on similar topics. I'll talk about his work through the talk, but he was one of the people who really inspired me to think about certain things, like how do you basically do large-scale measurement of internet filtering in the ways that I'll describe. And Royan Safi, who was a postdoc at Princeton for a couple years, also from Iran, so really not only had really interesting creative ideas that I'll talk about, but also brought some very personal stories to the discussion, and really made me realize how important some of these topics that we work on, and sometimes view, it's easy to view from a purely technical lens, but actually these really touch and affect many people's lives. So I owe a lot to both of these people for the work that I'll talk about. I've also worked quite a lot with several other students. Ben Jones, Frank Lee, and Paul Pierce are there, and then Vern Paxson, you might recognize, who's a professor at UC Berkeley. And then, of course, it's the requisite people I should thank as well, the NSF and Google. This work would not have been possible without them. So I wanted to start with a plot. So I think, maybe Philip and Amir and their students shouldn't answer this, but does anyone recognize this plot? Yes, good. So this was the internet going down 2011 in Egypt. This is internet traffic, volume of internet traffic on the y-axis, and on the x-axis we have time, right? So you can see basically at the time of political unrest, if you will, the government basically just said, well, we've had enough of the internet, let's just turn it off. And this basically happened for about 5 days. Without getting into sort of the reasons why it, eventually they turned it back on, which could be its own talk, maybe not even a computer science talk. I think it really sort of, at the time, raised this question, which is, this is interesting. Egypt was able to basically shut off access to the internet for the entire country in a kill switch-like fashion. And could we actually have that? Is it possible to have an internet kill switch? Could we shut off the internet? Could a government decide to do that for its citizens? We were talking about this in the U.S. at the time, just within a week after that, those events. And by the way, there was legislation in Congress to actually have this for the internet. Now, putting aside, the technical difficulties of actually doing that for a country like the U.S., which is sort of much more central to the internet than Egypt, reasons for doing this in the U.S. were ostensibly things like internet security, right? Like, what if suddenly we come under attack? Should we have the ability to shut ourselves off from the rest of the internet? Interesting, multiple layers of things to think about there, and I'm going to come back to some of those at the end of the talk. But of course, you can already see, that this is not an easy question. First of all, can we have these kinds of, is it technically possible to do this? How is it done, and should we have it? We often think of internet censorship as, a bad thing, or control of unwanted traffic, right? Spam, denial of service, phishing attacks as a bad thing. And I worked for many years on, there was even a conference, steps to removing unwanted traffic on the internet. So we'll come back to that later on in the talk. But that comes full circle. So before I get into some of those topics, let's sort of talk about what an internet kill switch might look like. What does that actually mean? Okay, so I want to unpack that. if we're talking about just kind of the basics of internet communication, who can talk to who. So we've got Alice who wants to talk to Bob, and Alice maybe is in the, I'll call it for simplicity, the censored internet or the censored network. That might be, well, you might think of the usual suspects, China or Iran or whatever, but it's probably anywhere of like upwards of 60 countries around the world behind some kind of firewall. And Alice wants to talk to Bob, but this censor is pesky censors in the way and might do things like prevent Alice from talking to Bob. That could be in either direction, right? So the firewall there, the brick wall, could prevent Bob from communicating with Alice or vice versa. So blocking traffic, and I'm going to talk about different ways that might occur. We'll talk briefly about how it happened in Egypt and then other ways that might happen. The other thing that I'll mention just right off the bat is that some of the powers that this censor has may not be purely technical, right? This censor could decide to punish Alice for trying to communicate with Bob. And that's going to come up again in the middle of the talk, because one of the things that's difficult for us to know, right, is what could get you in trouble, right? What is it actually okay for Alice to do? So hold that thought, and I'll come back to it. So how does this firewall thing get implemented? Well, there are a number of different ways. I should say, how does this disruption of traffic, this blocking, get implemented? There are a number of different ways. One of the ways is you can mess with internet routing, and that's what happened in the Egypt case. So Egypt had 5 internet service providers that connected itself to the rest of the internet. And on the y-axis, sorry, it's unlabeled, but I didn't make the graph, so that's okay, right? It's number of routes, like number of internet routes or prefixes that are advertised to the rest of the internet. And on the x-axis we have time, and each color is a different ISP. And what you can see, this is due to a company called Renesys, now Dyn, now I think somebody else even. Basically, you can see each one of these internet service providers slowly stop advertising networks to the rest of the internet. So even in this case, where things appeared to just kind of go dark quickly, you can see that individual ISPs were doing things, like specifically in this case, altering their routing protocol configurations to slowly take their networks off the internet. So a couple of interesting things, right? There are 5 different internet service providers, presumably acting under the auspices or direction from a government or a government agency. And it doesn't quite all happen at once, so it's not a monolithic thing, right? So this is one way that a, quote, kill switch might be implemented. Another way, of course, is with a protocol called the DNS. For many of you probably know this, but the DNS, the domain name system, maps domain names like NewYorkTimes.com or UMass.edu to an IP address. And if you can mess with that system or block it, right, then you can prevent, if you can prevent people from getting internet addresses from the names they're trying to look up, then that also can cause widespread disruption. And so yeah, Twitter blocked in Turkey, et cetera, et cetera. Okay, so I guess on the side of this building over here, we have DNS 8.8.8.8. Does anyone kind of want to take a guess at what's going on there? Sure. Yeah. It's Google DNS. So typically when you get internet connectivity, right, your internet service provider is offering that name resolution service. And in this case, like if, again, the ISPs acting on behalf of the government decide to mess with name resolution, then you maybe need to go elsewhere to get help resolving those names. And Google has a well-known server that will do that for you. So people were spreading the word that way. But okay, so now we've looked at 2 ways that sort of communication can be disrupted: routing and naming. Okay, so what I want to do now is sort of talk about some of our work in this area. So I'm going to break the talk into 2 halves. One is broadly under the umbrella of control of online speech. And the first question that I would like to talk about is, this question of who gets to speak, right? And this, I think, we sort of can think about as it's what the computer scientists, many of whom actually work here in the department, think of as filtering and manipulation of internet protocols, right? So the things we just looked at. The internet service provider messes with DNS, or they mess with internet routing, and by doing so, they prevent Alice from talking to Bob. It's that brick wall, right? Okay. I've also worked on other things like blocking of circumvention tools like Tor, but I'm not going to talk about that today. The second part of the talk, which I think is a increasingly important and very thorny question, both technically and otherwise, is this question of, well, one question is who gets to speak, but the other is who gets to be heard. And increasingly, who gets to be heard is controlled not so much by your internet service provider, but by online platforms, your search engines, your Facebooks, Googles, Twitters, your content distribution networks like Cloudflare, for example. And so the second part of the talk, I will talk about issues we've studied there and many, many, I think, unanswered questions and interesting things for us to think about going forward. So getting into this question of first, who gets to speak? A lot of things we can ask about filtering and censorship. And here are some of the things that I think that we could ask. How widespread is it? That's a multi-layered, tricky question. How variable is it? How does it change over space and time? The political scientists will tell you, that they know certain things happen on political anniversaries, Tiananmen Square anniversary, or around an election, or what have you. In order to figure out that something happened, you need a good baseline, right? So how are things changing over time? How is it implemented? Do they do routing? Do they do naming with the DNS? Do they do the standard firewalling thing? What, exactly how is it implemented? That can be really important too as we design tools to circumvent. What are some trends in this, not just in filtering, but in manipulation of information? I don't have the term in the talk, but I guess this, some might call, before the term was co-opted, the whole fake news business, right? It's not just about blocking, but it's about what's being said and who gets to see that. And then finally, what can we do about it? And I'm afraid I don't have the answer for those, so you can leave now. Okay, so let me get a little bit into this, the questions of measurement, and I think certainly this is a little bit. I feel a little bit like bringing coal to Newcastle here. There's some really fantastic people working in this department on topics that I'm going to talk about. Philippa's work on IC Lab is really outstanding and inspirational. I know Amir also has worked a lot on topics that relate to this. So. Regardless, here I am, and let's talk about some of these things. We read about these things all the time. These are old headlines. I could have pulled new ones. It's hard to keep up. And one of the things that I think that I observed as I started to think about this is that knowledge about censorship begins and often ends with anecdotes. And, so we see a news story like some of these, for example, and even more so, and then that's the end of it, right? And there's no data, right? So even more so, we see things like the Freedom on the Net report, and I know, Philip has worked very, very hard to sort of improve, some of the things like this, but. I would read a report like this, or you'd see a plot, or I should say a world map like this, and you see, okay, all of China is not free. The kind that they chose purple instead of red, I guess. But you talk to political scientists who know a few things about China, and you know that there's more than a few people there. And much like the US, there are different regions, and those different regions have different politics. And if you're talking about Hong Kong or the ocean cities, right, that's much different than what's going on in, say, the Western provinces, right? So how can you, and moreover, we know things are different around elections and political anniversaries and stuff. So how can you do this? Well, the reason part is because a lot of these reports, like before computer scientists started to get involved, were just based on kind of anecdotes, right? And at best, a smidgen of data here and there. Like, okay, Burma's having an election next week. Let's send in an activist. Oh, it's blocked. Let's color Burma purple, right? So what we want, and certainly I think it's no coincidence that many people in internet measurement, or at least a few, have gotten really interested in this is an internet measurement problem, right? Can't we get more than just these anecdotes? Can't we get better data on this? And so couldn't we say that specific services, rather than having a whole country a specific color, well, let's start with a specific service blocked in a particular country, better yet, maybe a particular region or by a particular ISP, and it was censored during this year, or better yet, like this week or this hour. And then how is it censored as well, right? So is it censored with DNS, routing? Does someone serve the block page? Many different possibilities there. And this turns out to be super hard. I think basically as an internet measurement person, it's easy to come in with some naive perspective here and say, well, surely we've got that firewall thing there. We can just measure this, right? Because obviously if Alice can't talk to Bob, that's going to be obvious. Okay, so there's this semi-famous quote, right? Someone said something about the internet views censorship as a failure and routes around it. And I think basically that is a totally false quote. I would rephrase that to censorship can be made to look like internet failure, okay? So, and often does, right? So Alice can't talk to Bob. Is that censorship? Well, I don't know. It depends on how you define it. Maybe it's a routing failure. Well, what's a routing failure? We just saw one that was like basically engineered. So on top of that, if you're talking about going to measure censorship in Iran, well, I don't speak the language, so that's going to be a problem. I don't know anybody there. Let alone, in the 200 countries and territories that we might be interested in talking about. So, lots of problems there. And there are a lot of different ways that this kind of censorship can take place. Now, sort of prior to our work, and I think a lot of censorship measurement kind of looks like this, right? Where there's an anecdote. Hey, Twitter's censored in Iran. Oh, researcher says, oh, let's go check it out. Basically there's custom measurement software that's deployed in those countries through VPSs, virtual private servers, through Raspberry Pis, through software running on people's laptops or phones or what have you. And then they measure it. And some of the best work on that is going on right here at UMass with the work on IC Lab. The Tor project also has something of this nature, basically where you basically doing that direct measurement. And that, I think, is really valuable because you can get direct measurements of what's going on, you can get packet traces, you can get really detailed information. But it's a double-edged sword because you've got to get the vantage points, right? So how do you, in order to get those measurements, you have to know people there. And if you do, then you're good. And if you don't, then it's a hard problem. So my student, Sam Burnett, started thinking about it. In fact, we were talking a lot with Philippa at the time, and at some point Sam decided that he wanted to graduate and decided it might be easier if we just didn't have to do that whole deployment thing. And he said, well, what if instead, couldn't we just deploy some custom software on the website? And then all we got to do is basically get website operators to volunteer, to deploy our stuff. And that's a lot easier because we know a lot of website operators. And then let's say anybody who happens to visit that page, becomes essentially a measurement vantage point for us. Okay, wouldn't that be a lot easier if you could just kind of turn the problem around? No more deployment problem, at least in the hundreds of countries where we want to go. All we have to do is get this software running on sites that people from those countries actually visit. And it so happens that computer science websites are pretty good for getting measurements from, say, China, Iran, India, lots of places that we might be interested in getting measurements from. That was coincidence. But the idea basically is turn the web browsers into a vantage point. And this works in a pretty simple fashion, right? So we've all experienced this, whether you think about it or know it or not. When you load any web page, you're loading embedded content of various kinds. You are loading ads. You probably know about that. You're also loading lots of other stuff, trackers, lots and lots of stuff. So basically what we did is we said on that website, let's basically drop an itty-bitty piece of code. It's, basically this HTML will go fetch some JavaScript and cause the browser to do something. And just like, your browser would load an ad, we'd have the browser, you can actually ask the browser to load anything, okay? So that's interesting. It's troubling in certain ways. I'll get to that. But that's very powerful. Let me first talk a little bit about how it works, and then I'll talk a little bit about how it doesn't quite work perfectly, both technically and otherwise. So the way that this works is, let's say on the top right, I've got a website where our piece of code is installed, and a web browser, user with a web browser visits that site, and colloquially, our piece of code will say, hey, can you access twitter.com? And then the browser will basically try to go fetch that content, right? It will basically try to go fetch an object from that site. So this is how ads load. This is how images and other third-party content get loaded onto any website. So just like anybody else can do this, we can do it too, and we can basically go ask the browser to go fetch something. We might be interested in knowing whether or not the browser can fetch. There's the reference to the paper. Now, there's a problem with this. There are a couple problems. Let me start with the technical problem. Web security has this thing called the same origin policy. Origin in this context means protocol, hostname, and port. It's a tuple, right? Browsers prevent a piece of code or software running in one origin from reading anything from another origin. So going back to this picture, right, if I'm running a website at Encore, I can ask the browser to go fetch the fave icon or whatever from Twitter, but I can't actually see what happened, right? I can't read that data. So that's a slight complication. But the good news is we don't actually need to read the data, right? The only thing we need to know is, like, did that work? And there are plenty of side channels in the web protocol that allow for that. The restrictions on resource embedding, actually, there are several of these that allow callbacks of different kinds. To give you an example, the image tag has a callback on load. It has another one called on error, right? So based on whether that image that we asked to retrieve from somewhere else succeeded with a load or failed with an error, we can have that browser call something, right? And through that callback, we get 1 bit, right? Okay. So that's basically how this works. And you can generalize this, right? So if we look at sort of what happens with Twitter, right? You do a DNS lookup, you try to connect with the protocol TCP, right? The transport protocol, and then you do a web request. Lots of different ways that, as I mentioned, that the sensor can interfere here. You could say, there's no such domain. You could drop the DNS request. You could inject something bogus, et cetera, et cetera. You could block the internet address, right? You could reset the connection in various ways. With URLs, you could match on a keyword and try to block things that way. And we can play games with fetching, trying to fetch different objects from the same domain. We could try to fetch a URL with the IP address instead of the domain name, and we can start to infer things about, okay, is filtering going on? Is it filtering the whole domain? Is it filtering the URL? Is it filtering the address of the server? Et cetera. So there are many ways that you can combine these requests to make inferences about both what's blocked and how it's being blocked. Won't get into the evaluation too much for lack of time, but we did do some case studies and where we knew things were going on and actually verified that that we were getting good signal from this. Okay, so that's the technical challenge. There's another challenge here, which is the ethics of this. And I don't have time to talk about all the considerations here, but needless to say, if we go back to the original picture, right, where Alice can get in trouble for even trying to talk to Bob, and now we've basically designed a system which is basically inducing Alice to talk to Bob's that might get her in trouble, a lot of questions come up on that. Okay, and that's very complicated. And one of the things basically that we have to think about is what can we safely measure with this tool. Okay, and I don't have a good answer to that one either, but I have some answers, some partial answers. One is that, remember what I said about, you're basically doing this whether you know about it or not, right? So it's hard these days to load many web pages on the internet without visiting certain sites like Google, right? You might not think you're going there, but many sites have Google Analytics, for example. Many sites have Facebook like buttons, right? Many sites have tweet this buttons. Okay, so any of those things is generating a request to Google, Facebook, or Twitter, respectively. Now, there's something in ethics called the principle of minimal additional risk. So if we can start to reason about, well, if by going on the internet, there's some likelihood that you're going to hit one of these sites anyway, then we can sort of hedge against those kinds of risks. These are not perfect answers. I don't think perfect answers exist, and I think this is an ongoing discussion. And I think basically this project started or kind of became public 2 years ago, and it's been kind of an ongoing process. And I'd say just now I'm happy to kind of say that the Computer Networking Community SIGCOM's newsletter, CCR, is going to have a quarterly ethics column that analyzes papers like this starting in 2018. So that was, I think, largely due to, shall we say, things we stepped in. Yeah, and I think, sort of half jokingly, I think this paper has probably been read as much by non-computer scientists as computer scientists. Pretty popular in the ethics and philosophy community as well. All advertising is good advertising, right? In any case, lots and lots of ethical considerations to think about when we think about the ethics of sort of co-opting another piece of the internet infrastructure that's not yours, right, to do measurement. I'm going to talk about another one of those now, which is filtering of TCP/IP. So many people in the room probably familiar with TCP/IP, given that one of the main books on it was written here. I won't get into too many details, but in case you've forgotten, TCP has a three-way handshake. Basically SYN, client connecting SYN, reply is the SYN ACK, and then basically there's an ACK. Important thing for that's basically if it works. If you talk to a machine where it's not listening to you, it'll send you a reset. That's the upper right. If you send the first part of the three-way handshake and you don't reply right with the third part, with the ACK, you'll keep getting the SYN ACKs coming back, right? So that thing you're trying to talk to will keep trying to talk back. The important part of this for this talk is this IPID thing, right? So thank you to packet fragmentation. Which doesn't really happen on the internet anymore, but thanks to that, we have this thing called the IPID counter. What that does basically is, for every packet that the machine sends, that counter will increment, okay? And there are different ways that this works, depends on the implementation of the operating system. But for some machines, this is a global counter, meaning like regardless of who it's sending that packet to, there's one counter, right? So we'll call that, it's like a global variable, right? So we'll call that global. Right, and that's going to increment for each packet sent. Now, here's the cool thing, and this is due to to Roy and Safi, who invented this idea, is that if that IPID exists, well, we can basically perturb that counter, right, by sending packets to that machine and causing it to talk back. That's cool, but that doesn't really help us if we're not in either of the locations that we care about. Like, let's say we're trying to measure, can China reach the BBC? And we're neither in China nor are we at the BBC, this is not helpful. But actually what's cool here is that if you can spoof traffic, meaning you can make it appear that it's coming from somewhere else, right? So I'm down here, right? And I can make my initial, so I basically am going to make it appear as though my packets are coming from the site over here, right? So I'm going to get basically replies, right? In this case, if the reflector is not listening, right, it's going to basically send back a reset, right? So that if I can make a packet going here appear that it's coming from over here, the reflector, then I can basically cause that counter to increment without actually being in either of those two locations. Okay, so I'll get into a little bit more detail on that because it works in both directions. But the system is called Augur. A couple things we need for this. We need, first of all, a measurement machine where we can spoof the source address of packets, make those packets appear like they're coming from say, the user in China, right? Without actually being there. That's tough. I don't have time to get into it, but like there are a few places where that works. But you need that. You need on the reflector side, the China side, if you will, the censored side, a global counter for this IPID thing. And on the site where you're trying to measure reachability, you need that property where there's an open port so that when you hit it with the SYN, it's going to start trying to talk back with repeated syntax. Now, if there's no blocking, what happens, right? So from the measurement machine, we spoof, right, with the SYN. Over here, what we're going to do, so the reset comes back. Okay. What we're doing there, basically, is measuring the increment, right? So we can see, basically, over time, if we talk to that machine up top, how's that counter incrementing? Because what we're going to do is look for acceleration, right? Because we're going to perturb it and then watch what happens. Okay. Then basically, then we start to perturb it from the other side. So we send step 3, we send a spoofed TCP SYN packet down to the site, and that site basically responds, right, to say, okay, yes, here's the second part of my 3-way handshake. Let me go that way. Now, if the reflector now sees that SYNAC, it's going to reply with a reset, okay? And that's going to cause the increment. And if that all happens as expected or without blocking, then steps 4 and 5 like get through, right? And we see a certain counter increment. We can then come back basically and then see our counter increment. Okay, this is a simplified example because there's other traffic on the internet, obviously. So I'm going to get to the statistical aspect of it in just a second. I don't know if that was your question, but yeah.
The question I wanted to ask is, does this assume that the amount of traffic coming out of the collection machine is fairly constant? There aren't bursts?
It's that's actually it doesn't, but it basically basically what we do is measure acceleration, and the reason that we do that, part of the reason we do that is we can assume a zero mean on acceleration and then perturb that. But yeah, so if you go for the 0th or even the first order, it's not guaranteed. Even still, it's not guaranteed. It's statistical, but we have a better chance if we're looking at acceleration. So this is sort of without blocking. Now, if the site to reflector is blocked, right? So that's sort of inbound into the blocked country, then our SYNACs aren't going to get there, right? Okay. So what's going to happen then? Well, essentially that site it never sees the reset, so it's going to keep retrying. Right, so now if we go down here and we try to measure the IP IDs on that bottom site, we're going to see a much faster, much bigger perturbation on the counter there. In the other direction, right, those basically what we can do there is we can sort of arbitrarily perturb to get additional resets and basically perturb that reset counter. Okay, so that's basically the mechanism of how it works. Your question kind of gets to this, but it's basically not deterministic at all. There are a whole bunch of, basically that's the basic idea, but noise is a huge problem. There's other traffic on the internet, I guess is the best way to summarize that. And the way that we deal with this is view that IPID counter as a random variable, the acceleration of that IPID counter as a random variable. So you can imagine if that machine is like a web server and it's getting some normal amount of web requests, then it's going to be seeing traffic at a certain rate, right? And it's unlikely that it's going to be accelerating at the same rate that we're perturbing it at. So by looking at those accelerations, we can sort of limit that, limit the uncertainty a little bit. So we treat the acceleration as the random variable, and then we basically we use statistical hypothesis testing to basically treat this as a detection problem, where again, so we're assuming that IPID acceleration is stationary and IID, and then we randomize the order in which we basically we do this at different machines. So we're not doing this at the same time of day, like for different machines, or the order in which we're probing the machines, and then we do it over a course of weeks to improve our confidence. That is where we are. I think basically what we can say and this is sort of the, just a highlighted evaluation in the paper. And I want to be very careful about this because this looks a lot like the world map that we started with. And I think basically there is more to do here. I think this is a sanity check more than a report, I would say, is that things look sane here as far as like the rates of blocking that we're getting. The paper has a lot more details about like the sites that are most commonly blocked in different countries, et cetera, et cetera. What we have not yet done and what's basically ready for the taking is to slice this by ISP. We are not doing this like 24/7 yet, although a new project with the Department of State and Philippa in the Berkman Center is basically planning to do just that. So we're still pretty early days here, but there is signal. Okay, so next thing is DNS filtering. So brief, or manipulation, I should say. So brief review of DNS, right? So the client wants to look up a name, right? There's a sequence of referrals, if you will. Eventually, that client gets an answer, right? These are iterative queries, but like eventually you get an IP address. Okay. Key point for this talk is that this is not secure, at least not in deployment. There are proposals to do so. So it's plenty possible for manipulation to occur. Okay, so why don't we just detect when it's manipulated, right? Because certainly like we know the expected answer for something like Princeton.edu or UMass.edu, and when the answer is different, we're good, right? We get some wacky looking IP address in Estonia or China, it's finished, right? Well, so this is due to a paper that measured the Google infrastructure from Ethan Katz-Bassett and his students. Well, so there's the picture of like where google.com resolves to around the world, and it's quite a few IP addresses. So this is an issue. In other words, there's not a single right answer. In many cases, there are a heck of a lot. And the straw man of, well, let's just look up google.com, and if we get an IP address in China, like that's it, right? It's probably manipulated. Well, that doesn't work, right? Because by design, it's returning IP addresses that are close to you. This is sort of the extreme example, but this is very, very common, right? Like pretty much any replicated service on the internet has some of this going on. So what we basically do is look for consistency, right? And there are different ways that you can talk about consistency. IP address is just one, right? So I've now just given you a counterexample for why looking for consistent IP address responses is probably not going to work out. But there are other things you can look for. You can map that IP address to the internet service provider that's hosting it. The autonomous system is often what we call map that to. That actually works pretty darn well. You can do other things. Doesn't work all the time, but it works a lot better than the IP address. You can fetch some content, right, and look at that content and see like, is it the same from different places, or is that different? That also not perfect, but it helps. You can look at the if it serves over TLS, you can look at the HTTPS certificate. Or am I getting the same certificate when I basically ask for the certificate? You can try to reverse map this thing and see like where it's going to, and is it like mapping back into a content distribution network like Akamai? And if it's, a bunch of them are and like 2 of them aren't, well then that's also a hint that something bizarre is going on. So there are a whole bunch of consistency metrics that we look at. The other thing you can look at actually are things that are independently verifiable, right? So, okay, fetch the HTTPS certificate and look, does the IP address, like, does that present a correct domain in that certificate, or is it like something, just some wacky domain that doesn't match at all? You can also basically do this. You can fetch it, based on the IP address. You can also fetch it using the domain name. So there are a whole bunch of different ways that you can do this. I'm skipping a little bit of the validation in here. I will just briefly say that these are roughly in order of effectiveness. What we do in the paper is just basically put them all together and say, if any of these things check out, like we'll just kind of say, all right, maybe it's not bad. And if they all fail, then we're saying like, okay, something weird is going on here. So we've just started to look a little bit at this in this first paper that I mentioned that was at Usenix Security in August, and Blue is, so obviously, oh, I forgot to mention a little bit of how we do this. There are some ethics that come up here as well. If we go back to our DNS picture briefly, there are these things on the internet, so there are these things called DNS resolvers. Typically you ask for an answer for one that's like close by. So if we're at Princeton, that server would be sitting at Princeton. If we're at UMass, that server would be sitting at UMass. Some of these are so-called open resolvers, and they will answer the query no matter who you are, right? So typically these are configured so that if it's sitting at UMass and you're like querying it from Princeton, that's like, it's just not going to answer you. But there are 22 million of these around the internet that will basically answer a query no matter who you are. Now, again, the question of ethics comes up here because a lot of those happen to be sitting in like people's home networks on insecure Linksys routers and things like that. So you don't want to really necessarily implicate users by sending bogus queries. The way that we deal with that is to try to ensure that the ones we're looking at are part of the internet infrastructure, and I won't get into how we do that, but we try to stay out of home networks and things close to the edge of the internet. By virtue of doing that, we go from 22 million to like 5,000 of these open resolvers that we can query, but they're still spread out in hundreds of countries. They are not evenly distributed, and that's the blue line. So there are a whole bunch more of them in, in the U.S. than there are elsewhere. But you can. So the interesting, the interesting thing here, the red line is the fraction of the responses that we issued to resolvers in that country that failed on all those tests, like all 7. Okay. So in Iran we didn't have as many places to query as we did in the U.S., but like a whole bunch of them basically failed on different counts. And again, I'll sort of skip over the specific domains that are implemented, that are manipulated in this way, and I'll sort of skip the graphic, that's in the paper showing some of the the heterogeneity of the results. But one brief observation I'll make here is that with this technique, in a country like Iran or China or whatever, there are tens to hundreds of DNS resolvers that we can measure through, and we are not getting the same answer from different, from different resolvers in the same country. So I know Philip has done some work on sort of implementation of block pages and blue coat devices and other kinds of firewalls. But going back to that picture at the beginning where I showed the kill switch isn't just one kill switch, it was 5, right? Well, even in these cases, it would appear that there are interesting heterogeneous, strange things going on. And I think we're still early days trying to figure out, like, are some of those inconsistencies where we see, okay, from this resolver in Iran, like Twitter appears to be fine, and this one it's not. Is that a vagary of our measurements? Or is that an ISP related thing? What exactly is going on? So lots more to do here. Okay, so that brings me to the part of the talk that's a little bit shorter, but I wanted to sort of talk about going forward. There's no need to really filter the internet if you can instead control it. Okay, so this, I've been thinking about this for some time, but this was really partially inspired by the work of some political scientists at Harvard, Gary King, Molly Roberts, and co-authors, who basically talk about censorship in China. And one of the main points of this paper, the title actually I think summarizes it quite nicely, is that we think about the Great Firewall of China as like, oh, this kill switch thing, but in fact, a lot of stuff gets through, right? And a lot of stuff gets through not because of implementation error, but by design. And the brief summary there is that, well, if we want to, the point isn't to shut off the internet, it's to like stop a revolution, right? So if we can permit some kind of discourse and control that, right, and allow certain kinds of criticism, as long as we sort of prevent collective action, we're okay, okay? So this comes to an interesting point, which is that it's not just about, let's just prevent people from talking to one another. And there's no need to do that if we can basically control like what we can say and who gets to be heard. Okay, and there are a whole bunch of different ways to do that. Through propaganda, right? Through pollution, and through different ways of implementing personalization, filtering, etc. Let me just briefly talk about a couple of those. Okay, so filtering. We looked at this problem in 2012. Okay, in other words, how can you basically determine that, or can you determine that someone who's sending tweets, or I don't know if it's a someone, an account that's sending tweets, are they aligned with, say, one political party or one dipole of a debate or another? So one thing we looked at basically is, we looked at a couple of these, a Senate race and a debt ceiling debate. I won't get into like all the details of the method, but basically you can look at the follower graph here and you can determine like what we did in this paper, I should say, is we looked at basically for any given node in this graph, like how close are they to a dipole or not? And you can basically measure this with graph conductance, okay? And it turns out like, at least, so this was 2012, mind you. This is different now, I think. I'm going to mention that. But one of the things we saw is that the solid blue and the solid green lines are sort of more extreme, if you will, in terms of like they're following one side of the debate or the other in terms of the follower graph. Repeater score is like fraction of retweets to tweets. So there's a real separation here. We did this. There are a whole bunch of these signals that came out at the time. Okay, so higher fraction of retweets. I just showed you that. More bursty tweeting volumes, higher daily volumes, and faster retweets. Now, I started thinking about this about 2-3 weeks ago, and I thought, well, the way that we did this at the time was by looking at the follower graph. But now, like, this is probably not. It's probably worth redoing because now there's so much more trolling and bots and other things that probably there are a lot more accounts now that follow things on the other side of the debate so that they can pounce, right? So this was a pretty easy labeling exercise 5 years ago, and I suspect that this is probably worth doing again. Okay. Another thing, so I mentioned propaganda. Another is sort of filtering and personalization, right? So here's a quote from Mark Zuckerberg. One of the several quotes that sort of caused me to quit Facebook. But the point here basically is, that he's making, and that Eli Pariser wrote about in his book, The Filter Bubble, is that we're each seeing our own version of the internet, right? Okay, and personalization, right, designed to do things like give you good recommendations on what to buy or what movies to watch, or what your friends are saying, or what search results you're really interested in when you search for shoes. Platforms hold a lot of sway over what you see. We built this thing called Bobble. What we basically did, this was back when Planet Labs still existed, if people remember that, but in a large distributed system, you could measure things like search results from a lot of different vantage points, right? So one of the things we did is take a query, we executed that as different users with clean profiles, different geographies, et cetera, different history, and looked at basically what showed up. And we built a tool called Bobble, where if you search for something, you could basically not only see your search results, but hey, here's some things in yellow that other people are seeing that you're not seeing. Okay, so that was one thing. So that was one thing we looked at. Now this is everything that was discussed about filter bubbles was like best case scenario, right? Like in the best case scenario, you're getting your own version of the internet. Okay, this filter bubble thing. Well, what about like web security, and where does that come into play? So it turns out, and a lot of these people talking a lot about sort of fairness and algorithms and other things these days, but one of the lessons I think we can sort of take away from that or sort of think about there is that algorithms, of course, are only as good as their input. And one of the things here that I'll show you is like, let's search for shoes. Okay, so Google's going to give me some personalized results. Right now, my search history is empty, right? So great, the only thing in there is shoes. Excellent. So what I'm showing here, right, is that we're looking for a particular result, looking for Macy's shoes, and it happens to be on the second page. Okay, so there it is, shoes at Macy's. Okay, so what happens now? Next thing the user's going to do is visit some other site. Okay, boom, it's a muffin, as it turns out. There it is, beautiful. There is something you can't see there, much like Encore. There is a cross-site request there. What happened was upon visiting that site, which I control, the search history is polluted, right? So we did, if you're logged into Google, who logs out of Google, by the way? Right, there's stuff in the search results, right? So I put in Macy's shoes. Now, when the user searches for shoes, there it is right there on the first page, right? So simply by virtue of being able to do things like Encore and other things like control what the user's browser is doing, you can actually do things like pollute search history and control what people get to see, right? So lots to think about there. Final thing I wanted to talk about there in terms of like controlling, who gets to speak is automated filtering algorithms. And this kind of comes full circle with what I started to talk about at the beginning, which is like filtering unwanted traffic. And I actually worked a lot on this like 10 years ago. I thought like filtering unwanted traffic, that's like a good thing. Spam, we don't like that. Let's get rid of that. And one of the things we worked on a lot, and I think this is, again, something to sort of, it comes full circle, is a lot of people were looking at content and IP addresses. And one of the things that we sort of thought about hard in that work was like, well, you can identify spam without really reading, or looking at the content, right? Which has obviously got problems of its own. You can do things like look at the AS of the sender's IP and like how long is the message and what's the geographic distance that thing is traveling, and just like anything these days, you can throw it into a big classifier and good stuff comes out. And that's what Shuang Hao did back in 2009. And we thought this was pretty cool because at the time, people were doing this manually and with content. And this is really hard. We can't like do automated detection, et cetera, et cetera. And we thought we were pretty proud of ourselves. And then we took this to a large mail service provider, and won't tell you which one. And we were like, yeah, this is pretty good. Look, detection rate 70%. That's as good as Spam House. Totally automated. False positive rate 0.44%. That's pretty good, right? And they were like, this is totally terrible because that's only like that's 4 in 1,000, and that's like 4 in 1,000 like job offers like going into the trash bin. And by the way, it's not just a user experience problem. This is a First Amendment issue, and this is a speech issue. And I was like, oh, interesting. Security runs up against the First Amendment, and that's basically, I think, kind of like where things are starting to come full circle. Because we solved that problem, by the way. You can, in a practical setting, you can sort of cheat, right? Anybody who's worked on machine learning knows that you can turn a dial and kind of get that down to where you want it. So like once you get the automated filters to like get all the bad stuff out, it's all good, right? Like problem solved, like internet secure, et cetera. Except now, right? Well, we can design these automated filters to do stuff like filter spam and child porn and everything, right? So great. So let's just like take down beheading videos, right? Let's take down terrorist speech. Let's take down copyright. Like you guys can do that, right? There was let's see if I can play this. This is like 10 seconds. This is Hani Farid, who designed Photo DNA, which is one of the things that's basically used to match child porn images against a known database. Oh, that didn't play, so I may not be able to. Let me try. Oh, sounds good to me. Basically, what he's saying, it's summarized here, is that yeah, these tech companies, these computer scientists, we like know how to do this, right? Like we know how to do automated filtering. Like I invented Photo DNA, right? Like I can match images against the database, and we know how to do spam filtering. And yeah, they just know how to do this. They're just like not working hard enough, right? And so we're starting to see stuff like this. Sounds good. Stop enabling sex traffickers Act of 2017. So who wouldn't want that, right? That sounds really good. What this says, there's something called the Communications Decency Act, Section 230. What that talks about, that law, says that intermediary service providers like Google, Facebook, YouTube, Twitter, et cetera, are not criminally liable for the content that they host on their platforms. This, by many counts, has been responsible for the resurgence of a lot of innovation. By the way, if you start your own company where you're going to host other people's content, whether that's the new Craigslist or some other social network site or a blog or what have you, you might be happy about the Section 230 of the Communications Decency Act. Well, this bill, which is basically working its way through the Senate right now, is to remove safe harbor, if you will, from the intermediaries like Google, Facebook, Twitter, et cetera, for sex trafficking. Sounds good. There are a couple things, though, and you start to realize maybe why this might not be 100% good when you look at the supporters of the bill. One of them being the Motion Picture Association of America. So any ideas what's going on there? So the argument, right, is that, well, if you can do, surely you guys like can automatically take down sex trafficking, backpage.com ads. Like, well, why don't you take down all this pirated content too? And why don't you take down these other things, right? So what we have now, it's not just about, like censorship and filtering and preventing who could talk to who. We have these platforms, right? Google, Facebook, Twitter, et cetera. And they hold a lot of control over what we're going to get to see or not see. And by the way, there are laws being written that might actually have something to say about that too. Another thing I wanted to just briefly sort of mention is that that it's not just the Googles, the Facebooks, the Twitters, and the things that we hear about all the time, but also our content distribution networks, right? So Cloudflare, right, made a decision some time ago. And I think Philippa has actually worked on studying some of this, as well as, a lot of attack traffic comes from Tor. Well, let's just block Tor, okay? By the way, yeah, we don't really like hate speech either, so we'll just like take those guys down as well. Whether or not you agree with what these people have to say, Daily Stormer, by the way, in case you missed it, is like some neo-Nazi propaganda news site. I don't know. In any case, I'm sure that basically all of us, violently disagree with what they have to say. But regardless of what, where you stand on that, there's definitely something to think about there as we think about a company like Cloudflare and their ability to say, well, we don't really think you should be able to see this anymore because today it's neo-Nazi propaganda, and what is it next, right? Now, coming back to the sort of automated filtering, right? Spam, I worked on that one. Phishing, I worked on that. Child porn, like people have worked on that. But this general problem, even technically, is a lot harder because context matters, right? Well, there might be a great algorithm to detect, a beheading or ISIS flags or things, but how do you know it's not parody, right? Or I might be able to, very easy to fingerprint, an image or a movie clip or a song clip against a database of known copyrighted content, but how do you know it's fair use? Technically speaking, from a technical perspective, can we solve these problems? I don't know. I'm told deep learning can solve everything, so maybe we'll get there. But I think basically this brings me to kind of where I want to end, because there's a lot of really hard, interesting technical problems here as far as like what, let's figure out what's possible. But the internet's like much, much different from when we had like, when it looked like this, right? This network of trusted universities, few stakeholders, no security concerns, a single government. Now it's just like way complicated, right? You've got like ISPs and content providers battling it out, attackers, battling it out with law enforcement, governments. We've been talking a lot about that. And now networking is not just about protocols, it's really about economics and policy and security and privacy and human factors. So good technology is really not enough, right? Now we've really got to be thinking about all of these things. And I have to say, when I first wrote my first internet censorship paper in like 2002, I was like, well, this is a cool like technical problem. I'm going to build like covert channels into HTTP. Like, this is awesome. And I don't really, whatever China thinks, that's their business. I'm just like designing cool technology. And by the way, you'll still talk to people who have that view. And I really don't think that that's the case. I think as technologists, we have to both consider the broader ramifications of the technologies we design, but also we need to be at the table where a lot of these decisions are being made. So on the first topic, right, like going back to that automated filtering question, what's technically possible? Well, we can find out. We can evaluate that. We can learn about it. We can also improve that. We can push that boundary, and I think that's what we should be doing. We're very good at that. I think the place where we have a lot of work to do is stepping out of our labs and also talking about and explaining the current limitations of technology to people who are making decisions about these things, because we're all relying on it. So thank you.
map for that. Am I reading this correctly that the U.S. has 1.2%?
What's likely going on there, companies, right? I mean, there is filtering in the US too, right?
I'm just comparing it
yeah.
with some of the most, well, non-democratic.
One of the things that's going on there is company firewalls and other things like that. So we haven't basically sliced it by that. And the other thing that's going on there too is that we also have a much larger sample in the US. So yeah. Yep. Good question. I would say. Oh, that basically means that's the percentage of sites that we basically saw filtered with the TCP/IP based testing for any client in those countries. So like. Yeah, yeah. So I think basically, actually, let me treat this as an invitation. So a lot of the tools that I discussed have data sets behind them, and there's a lot more slicing to do. So there are a whole bunch of things where this bears slicing in different ways. By ISP, so we could talk about by company or by ISP or what have you. We can't do it by time yet because we're not doing it longitudinally yet, but that's coming. Another thing basically that we have talked about is what does this look like to certain destinations like Tor bridges or VPN providers? Or what does this look like from a refugee camp, for example, where a lot of censorship is known to take place? Yeah.
Sorry to keep you on the slide, but
absolutely.
There's several variables here, right? There's a computer in a
yep.
country, and then there is something that's actually like a computer tries to go to Google.com, or
yep.
go to Facebook.com, and then you're seeing whether it's
yep.
So have you looked at the sensitivity of the Google.com or Facebook.com, the thing that the computers are trying to access? Like if you give it different websites, do you get vastly different numbers?
We have looked a bit at that. So I will tell you that basically using just the value of the counter does not work at all. So I mean that's basically where we arrived at acceleration as something that's relatively stationary. It varies a lot. Like the increment value varies a lot by site.
Yeah. It's not just that, right?
Yeah.
You could find that China only blocks Twitter, for example.
Uh-huh.
So if you're
yep.
checking for how many computers block Twitter, you get a much larger number in China than if you're checking how many sites block Facebook.
Yeah. You're right. Yeah.
So did you vary the what is blocked or not?
Oh, what's our test list?
That's right.
We use the same test list in all countries.
But have you looked at if you change the test list?
Yeah.
Does it have a huge impact on the
good question. Haven't looked at that. It's the Citizen Lab block list. So it's I won't say that it's large, huge, but it's
Well, so these are actually overestimates over average traffic.
Yeah. Yep.
Inside
These are yeah. Yeah.
So there's a push to sort of encrypt everything and have HTTP
Yeah.
everywhere.
Yeah.
Do you see that and things like CDNs affecting, I guess, censorship going forward?
Certainly. So I think one place where you could see that, something I didn't talk about, is keyword-based filtering, right? So for example, it was certainly the case for quite some time that at least China and probably other countries as well were, and by the way, I'm not an expert on keyword-based filtering. That's, I think Jed Crandall at University of New Mexico has basically studied that a lot. But, basically these filters would look for things like, Falun Gong or free or something, freedom or something like that, and then send resets based on that. So if that's, if we're talking about HTTPS where the URL is encrypted, like that's a problem. Also, obviously, the content's encrypted. That's a problem as well. Obviously, there are lots of papers in security about like, can you fingerprint the site, et cetera, et cetera. So, but I have to imagine those are like way too involved and uncertain and difficult, like way too expensive for most countries to do. It's just much easier to mess with the DNS. Thanks. There- Mm. There were a couple different questions in there. So one was, the broader question is, yeah, what's the right outcome? And then there were a couple of different things about, like one was about manipulation, another was about blocking. So so I think, I need to think about that. So it's complicated, right? Because countries are sovereign, they have laws, right? If I didn't talk about circumvention at all in this talk, right? But certainly enabling the use of circumvention technology, may be running afoul of laws in certain countries. So I didn't go there, conveniently, perhaps. Let me come back to the question of ethics and legality of measurement, which I think is a little bit easier. Still not totally tractable, but from a legal perspective, we just really don't. Often we don't know what's legal, and it may be a question of, well, there's no law. And in fact, this is where we started. Was like, oh, there's no law written down that says you can't do this, right? So clearly we can do it, right? Well, except you could be thrown in jail for tax evasion or something else. So then it becomes an ethical question. From the measurement side of things, with ethics, complicated. The main thing you want to do is basically not put users in harm's way. And actually, the really hard thing about that in this type of work is that we don't really know that we aren't. The things that I mentioned are not foolproof, right? So I said, oh, we're going to try to send our DNS requests through things that look like infrastructure. Well, let me give you an example, like AWS, like an Amazon server. Well, that's not at the edge of the internet. Well, but it's rented by someone who is. So not perfect. I don't have a good answer for you even on the measurement side of things. What do I think should happen as far as access to information? I think I'll punt that one a little bit. But I will say, like coming back to the the sort of topic of a lot of what I talked about, one of the things that I think really needs to happen is that we should have, particularly, now I'll speak sort of as a US citizen here, and I know the Department of State is in particular interested in this. We need to have better information about what's going on in different places, right? Because that's a diplomacy issue, that's a national security issue. So you can view this as intelligence in a way from the perspective of the US. So I guess that's as far as I want to go into value judgments. But yeah.
What do you think about the future of circumvention tools? Because in my mind, I think nowadays to invent a protocol it could take years, but to block it with the help of machine learning or something, you can truly block some kind of protocol. So I think basically the government can put a lot of money into training the model in how to define all kinds of algorithms.
Yeah, that's an interesting question. I think I again don't know the answer. I do think that you're right that it's a losing battle for the reasons that you mentioned. Let me sort of suggest that maybe there's hope. Okay, so I mentioned the work from Molly Roberts, the political scientist. Another piece of work that she's done, which I think is quite interesting, is that she's observed that like an increase in blocking and censorship can actually in some cases lead to more access to information. So now that's counterintuitive. So what's going on? Well, a country decides to block Twitter. Now all of a sudden a bunch of people learn about VPN software and they start using it. Okay, so it's a bit of a cat and mouse. Then the VPN gets blocked, but essentially what happens is like by blocking something, you in some cases draw attention to it, and you also sort of educate your population about ways to get around the technology. So I think one of the interesting things that these political scientists have observed is that maybe turning the dial up to 11 on censorship and filtering isn't always the best thing anyway. That's probably not the most satisfying answer because I don't think like it doesn't mean we're going to win for whatever that means. But I think you're right that it's a bit of a losing battle. I mean, Tor is blocked in many countries, and I don't think there's a way around that actually at this point. Not today anyway. And you're right. I think currently the trends are not working in our favor. Yeah. So let me see if I can understand. Your question started sort of asking about ICANN and basically how it's transitioned from U.S. governance to a multi-stakeholder kind of setting. Can you connect that again to the sort of, the Cloudflares and the Twitters and the Facebooks? Why does it matter? Ah, okay. If the majority of people, okay, so there are a couple of different questions in there. Let me first just briefly mention the ICANN thing, and then I think your question's about something a little bit different. So ICANN, of course, deals with the allocation of names and numbers to countries and internet service providers, et cetera. It's a fairly bureaucratic process that involves allocation of, as the name would suggest, names and numbers. There's some there's very little reason why we kind of need to retain control over that, given that there are often benefits from a policy perspective of those kind of decisions being multi-stakeholder. From a technical perspective of who gets access to content, that decision is almost orthogonal, right? And maybe that's your point, is that okay, ICANN's now the people who decide who gets, to run .com or who gets this region of IP address spaces, that's multi-stakeholder. But that actually, in some sense, if everybody's going to these 4 sites, that really doesn't have anything to do with, how IP addresses are given out. Why should we care? Yeah, so in some sense, yes, we shouldn't care about the ICANN. I think we shouldn't be so alarmed about that development for completely different reasons. I do think that the centralization of how we access information to a very small number of sites is the more alarming, development. Is that where you're headed? Okay. Yeah. Yeah. Thanks.